going through chapter 5, chapter 6, I want you to realize that there's a pattern to it. In chapter 5, the first things that we looked at were, first off, how do you collect data? And remember, we talked about things like observational versus experimental, and we talked about a variety of different ways that you can do experimental, different ways that you can do observational, okay, like the case control studies versus just doing an experiment. Where do you use the case control studies? What kind of situations do you use those for? Okay, the case control is something like wanting, yeah.
Like texting and car crashing.
That's right, okay. Is it safe to drive up and down I-75 during rush hour while you're texting? Well, we could take 100 people and turn them loose on I-75, texting during rush hour. Is that really a good thing to do? No, because somebody's going to die, aren't they? Oops, we had 3 deaths. Too bad for them. Okay? That's not the way you do that kind of stuff. So what you do is, instead of putting people's lives in danger, you look at the records that are already out there from people who decided, well, I'm just going to do this quick text and, ooh, I'm going to buy the back end of a truck at the same time. Okay? You look at the records that are out there and you base the conclusions off of analysis of the data that has been collected by people of their own choosing, partaking in whatever that activity or behavior is. Okay? So there are some situations where you don't want to endanger people's lives, intentionally. It's their choice if they're going to do it. Okay, case control. Observational stuff where you're just looking at it and writing down what's happening. An example of that is how many people like to use the revolving doors versus the doors that just swing. Well, you could go down to Cincinnati, sit in the lobby and count how many people come through the revolving, how many come through the swinging doors. Make sure you talk to the manager first and get their approval so that they don't think that who knows what anymore. Okay, so they know what you're doing. But those are observational studies where you're just looking and you are not in any way affecting the people's decision making, their behavior, or whatever. Experimental is where what's an experimental design for data collection going to basically look like? That's kind of like something where you give part of the people a treatment. The treatment might be a sleep regimen where you make sure they actually get 8.5 hours of sleep a night. Whoa, there's a thought. And compare that to people who are getting 5 and 6 hours of sleep a night. Or you give some people a specific medication and you give other people a placebo. Oh yeah, remember what are placebos anyway? That's a fake pill, isn't it? Usually like a sugar pill. Doesn't really have any effect, but the idea is mentally they're still getting something. Okay, so you don't have the psychological aspect coming into play, because there are some people who get better when you give them sugar pills, just because they think they should be getting better. The psychological aspect of sickness is significant. Okay. So we talked about how do you collect data. We talked about how do you display data. We talked about various types of graphs, various ways to organize it, binning the data. Okay, if you have times, like for swimming trials, if you were to list every time separately, you'd have a whole bunch of separate pieces of data. So you could collect them all up, and everything that was a 5-second swim, everything that was within the 6 seconds, 7 seconds, you bin it, okay, collect it up into different groups, and then you graph it. We talked about graphs that are appropriate for qualitative data versus graphs that are appropriate for quantitative data. Okay, so first thing was how do you get the data? Second thing is how can you kind of organize it? The third thing then was how can you start to talk about or describe the data? And that's where we did the 5-number summary, where we did the standard deviations. Okay, now I have on several occasions talked about the wonders and the good things about standard time because I really want to get through. One of the advantages to standard deviations over a 5-number summary is if you have data that is normally distributed, it's in a bell curve shape, where the most common occurring observation, it may be tire wear, okay? The most common is for this set of tires to last 60,000 miles. It winds up that the mean, the median, and the mode, so I'll do the mean, the median, and the mode are all right there. It happens, it's okay. Okay, all three of them are in the same spot. The cool thing about standard deviations is it doesn't matter how big the data might be. If it's normally distributed, x bar, which is the mean, will always be in the middle. This one standard deviation in either direction will include what percent of the tires, the light bulbs, the people, the whatever it is you're looking at. One standard deviation will always be 68%. Okay, and that's a useful number to keep in mind. If you move out 2 standard deviations, that will always account for 95%. And if you move out 3 standard deviations, that will always account for 99.7%. Doesn't matter how big the numbers are in the data. If we're talking about tire wear, one standard deviation may be 5,000 miles. If we're talking about weight gain or weight loss, one standard deviation may be 5 pounds. Okay? So realize the size of the numbers, whether it be 5,000 or 5, does not affect one standard deviation. One standard deviation will always work based on whatever the size of the numbers is. One standard deviation will always give you the 68, 95, 99.7. It'll always work. And it's a pretty cool deal because you get a whole lot just by doing the standard deviation. Okay? That's why it's such a popular statistic to look at with regard to data. Okay, so we then looked at what are some ways to find kind of the average, kind of start to describe the data, describe what you would expect to have, and that was the 5-number summary and the stuff with the mean and the standard deviation. Once you get your standard deviations squared away and computed, you can then start to talk about where is a specific tire's performance, a specific light bulb's performance, a specific person's score compared to everybody else. And to move into that comparison is where we're going to use this table that I kind of wrote on. Okay? This table talks about z-scores. What we're going to want to be able to do is with a specific piece of data, compare that to everything else in the distribution and answer the question, how well or how poorly did this one do compared to everybody else or everything else? For example, Monday I had a checkup. Okay, my blood pressure was 96 over 64. What is the average blood pressure for people? Average is around 120 over 80. So this says my blood pressure is higher than lower than the mean blood pressure. It's lower. is having low blood pressure a good thing or a bad thing? It's a good thing to a point. If it's 20/10, you're in trouble. Okay? But to a point, it's a good thing because that means that the circulatory system is under less pressure, less stress. That's good news. Okay? They also took my resting heart rate. You know, where you're just sitting there and they count or whatever. Works out to be about 50 beats per minute. So I checked for my age group. Okay, I'll tell you. I just turned 62. Okay, so you're not there wondering, his age group. What age group is he? Is he older than dinosaurs? Is he? I was bringing that up. I used to teach middle school and stuff, and those kids are a riot because they haven't really quite figured out ages and things like that. And one student one day, dead serious, asked me, Mr. Emenacker, what was it like when dinosaurs were here? So I informed him the last one died about 2 years before I was born. Anyway, so my blood pressure beats per minute is about 50. And I looked it up. For 60-year-olds, they don't list for 62. 60 is close enough. Okay? About the lowest pulse rate is 46, and this is classified as athlete. I'm not quite sure what a 60-year-old athlete looks like. Okay? Okay? But mine was at 50, and it puts me in the bottom 5%. What do they mean when they say the bottom 5%? The bottom 5% of what? Well, of all the 60-year-old people in the United States, 95% have a pulse rate that's faster than mine. 5% are at or lower than the 50 beats a minute. Now, I bring this up because it's an illustration of sometimes you want to be average. For example, the average person has how many arms? 2. How would you like to have 5? Think of everything you get done with 5 arms. And you're looking at me like, yeah, right. Would you like to be above average as far as the number of arms? Yeah, probably not, because everybody's going to be... And that's not the kind of attention people usually like to get, is it? Nah, that's not the kind of attention, we'll skip that, okay? So there are times that you want to be above the mean. There are times that it's nice to be at the mean. I'm glad that I've got the mean number of arms. I'm glad I don't have 3 eyes. Because then I wouldn't wonder when I'm teaching, are people looking at me because of the eyes? Or okay? You get it. There are times that you want to be at the mean with pulse rate. Is it a good thing or a bad thing to have that slow of a pulse rate? It's actually a good thing. A low blood pressure and a low pulse rate are typically indicators of being in pretty decent shape. Okay? My son is in really good shape. They work him to death out there with the hockey. His pulse rate's down, resting pulse rate's down in the 40s, which is like marathoners. Okay? If your pulse rate's up in the 70s and 80s at a resting rate, that's a problem because your heart's working a whole lot harder than it needs to, which says what about your lifespan? Probably not real good. Of course, nobody knows when God's going to reach down and say, Chuck, you're done. Okay? But we're just kind of playing the odds, aren't we? Odds are if your pulse rate's lower, you're going to live longer. So I told my wife, I said, she's stuck with me for a long time. Sorry. Okay. Realize that on the different measurements, there are times that you want to be at the mean, times where it's desirable to desirable to be below the mean. Now, how do you measure how far away a specific value is from the mean? How do you figure out percentage-wise where that value is? Well, one way to do it is with z-scores. With a z-score, this is a formula you need to know, okay? To compute the z-score, what you do is you take whatever the data point is that you're interested in. From that, you subtract what the mean value is, not the median, not the mode, the mean value, and you divide it by the standard deviation. And that'll let you know percentage-wise where a particular value is. And contextually, you can figure out, do you really want to be at the mean? Do you want to be above or below? The other day, I believe we did this one. Is that accurate? Okay, nope. Okay, good. Then we'll take a look at this one. Cholesterol. Good thing? Yes, ma'am. Sure. Actually, it's right here, too, if you want. So you can get it in red off of the slide, or you can get it in green off of the board, your choice. Okay? Whoa, decisions. Okay, cholesterol levels. Is that something you want high, low, or average? Average or a little bit low is not bad. Does your body need cholesterol? Yeah, there are a lot of chemicals that your body uses as a building block to make chemicals that your body needs. It's just that some people have more than what they need, and if you've got too much, where does your body wind up storing it? In your blood vessels, and it gets hard, and your blood vessels get hard, and if your blood vessels can't flex, they can break. They're called aneurysms and things like that, and they're not good. Okay? So you want to keep the cholesterol within a given level, a level that is normal so that your body can produce the things it needs, but it doesn't have to store extra. Okay, so we're given some information. Men, 18 to 24 years of age, mean cholesterol level, 178, standard deviation, 41. 20-year-old man goes in, gets a blood draw, they run a cholesterol check, and that person's score is a 190. Now, is this something you want to score higher than normal on? And yeah, baby, I hit it. I've got a 270. That's not where you want to be on this, is it? You don't want to be there at all. You want to be right about the mean or maybe a little bit low. To understand what a score of 190 means compared to everybody else, what we're going to do is we're going to compute the z-score. Well, you take whatever the data point is, subtract what the mean value is, and divide it by the standard deviation. How much spread is there in this information? This will give us then 12 divided by 41 equals, and let's see here, if I do 12 divided by this 41, it gives 0.29. Okay, so what does 0.29 mean? Well, by being positive, it means we're a little bit to the right of the mean. If you look at the bell curve, a z-score of 0 puts you right in the middle. This z-score being a little bigger than 0 is going to put us somewhere over here, which is going to put us in the upper half, isn't it? How far into the upper half is this person's cholesterol level? Well, let's go back and check. 0.3 is about as close as we're going to get. The percentile is 61.79. For quizzes and tests and stuff like that, I'll provide one of these. You don't have to memorize it. Oh, that's good news. Okay? 61.79. Well, what does that actually say about this individual? What it says is that 61 0.79% of all men in this age group have a cholesterol level that is lower than this person's cholesterol level. This would mean that if we call this, is it okay to round this to 62% here for a quick example? That would mean that 38% of the people have a higher cholesterol level. So this person's cholesterol level is starting to get up there a little bit, isn't it? A little bit above normal. They need to start considering statins and stuff. I guess it depends on what else is going on in their life. Okay. But it puts them in the top 38%. The question can be posed the other way around. Okay, what cholesterol level would put you at the 90th percentile? Now, if you're at the 90th percentile, that means that 90% of the people have a lower cholesterol score, which means you're in the top 10%. Does that make sense how the two tails work? Okay, we're going to keep going after that. To figure out what the cholesterol level would be, we're going to do the z-score, which is the data point. Well, we'll call that our cholesterol level, minus the mean, divided by the standard deviation, 41, equals, now here's where things get a little tricky. We want a z-score, because that's what this computes, isn't it? This formula computes a z-score. And we want the z-score that is going to land us at 90%. What I'm doing is I'm looking at this column here, the percentiles, and I'm shopping for 90. Aha, here it is. To get to 90%, the z-score needs to be a 1.3. Does that make sense to everybody? Now that we know what the z-score is, we can put that number over here on the right-hand side, a 1.3. At this point, can we solve that for the cholesterol level? Okay. Yeah. What's the first thing you're going to do to solve for this? Maybe multiply by the 41, and that'll give us our cholesterol level minus the 178 equals, when we multiply by 41, we get 53.3. Then, to actually solve for the specific cholesterol level, we're going to add 178 to both sides. So that's going to give us our 53.3 plus 178. Whoa. Is a cholesterol level of 231 kind of high? Yeah, that's getting up there. That's the time where the doctor raises their eyebrows and says, you know, we may be talking statin time, something or other to get this back down. Okay. Does that make sense how to work those z-scores? We're going to do some more here. Okay, so that's not the last one. I want to make sure that this makes sense. Okay, let's take a look at another one. Different situation, different measurements. This time, instead of using cholesterol scores, which are around 180, I'm going to use the heights of women in the United States. 180 inches does not describe the height of an average woman, does it? That'd be about 15 feet tall. Yeah, that's a little taller than normal. Okay? What you're told here is that women ages 18 to 24 have a mean height of 65 inches. That would be 5 feet 5 inches. Whether you're taller or lower, whatever. Okay. Standard deviation, 2.5 inches. In order to serve in the military, in the Army specifically, the height has to be between 58 and 80 inches. So we have this range of heights. And you're asked then, what percent of women are ineligible to serve based on their height? Now, we've got to be careful because when we're working with statistics, sometimes you want to answer the question, what percent can serve? That may be the easier one to compute. In some cases, what percent can't? Okay? We're going to do some of each here. And the thing to keep in mind is, if we figure out what percent can serve, let's say 97%, yeah, 97% can serve. If 97% can serve, what percent cannot serve? 3. Great. So that makes sense. If you've got one side of the argument, it's easy enough to get the other side, isn't it? Okay? So sometimes we're going to get the side that isn't going to answer our question, but it's easier to compute. And then from that percentage, we can easily get the other percentage. Well, we have the information here to compute z-scores, don't we? We have the mean, we have the standard deviation, and we have our data points. Let's compute the standard deviation, well, the z-score, sorry, for 58 inches. So that's going to be this 58 minus the mean of 65 divided by the standard deviation 2.5 equals. Okay? So if we do 58 minus 65, that's going to be a negative 7 over 2.5, and a negative 7 divided by 2.5 is going to give us a negative 2.8. That negative is important. What's going to happen is, once again, we're going to go back to the bell curve, normal distribution. By saying that it's negative, all that means is we're to the left of the mean. So that lets us know which side of the curve we're working with. Does that make sense? Let's go back to the z-table. Negative 2.8, wow, that's 0.26%. Notice this is a percent. We don't have to change it to 26. It's already the percent. Okay, so when we figure this out, this is going to give us 0.26%. On the z-scores, and this is important to catch, the z-score will always tell you how much is to the left. What this says is 0.26% of the people, of the ladies in the U.S., are shorter than 58 inches. That's not a huge percentage, is it? Okay. So about 0.26% are going to be shorter than the 58 inches. Let's now do the z-score for the 80 inches. How tall is 80 inches anyway? Any idea? 6 feet is 72. 6'8". Yeah, 6'8" is pretty tall. Okay? Some friends have a daughter and she's 6'3", which is kind of weird. Well, not weird. It's kind of interesting. She's one of the few women I walk up to and see eye to eye. Unless she's wearing her work boots, then she's 6'4", and she's got an inch on me. Okay? When we do the 80 inches, we're going to do the 80 minus the 65 divided by the 2.5, which is going to give us here, looks like about 15 over 2.5. Well, that's going to be 6. A z-score of 6 is way over there. In fact, if you take a look on the table doesn't even go to a z-score of 6. it only goes up to what? 3.5. Okay, well, what are we going to do? Well, to get all the way down to 6, I'm going to kind of guess. In the book, they don't guess, but I'm going to say, this might be something like 99.99. All I did was I boosted it an extra 100th of a percentile. Not a big train wreck either way. Does that make sense? If you want, you could say, I'm just going to use the last number that's on there, 99.98. That's fine. I don't care. What this now says, remembering z-scores always give you to the left, this now says that 99.99% are to the left. If that much is to the left, how much is over here on this right tail? Do you buy that it's going to be 0.01%? Does that make sense? Do you see how we're looking at both sides of the story again? Now, we've got the percentile for each of the little tails figured out. And we're concerned about the people not who are eligible, but who are ineligible. The ineligible are going to be this little section and that little section. Does that make sense? So the ineligible is going to be the 0.26% who are shorter than what the military would prefer, and the 0.01% who's taller than what the military. They may not even fit in a Humvee. Okay? Wouldn't even fit in a Hummer. Total percent who are ineligible, 0.27%. Does that make sense? If 0.27% are ineligible, what percent of women, based on their height, are eligible? Well, we've got the 0.27%. Now we need to get the other side, don't we? And that's going to be the 99.73% are eligible based on height. So that's basically anybody, isn't it? Out of every 10,000 people, try and put this in a different perspective for you. Out of every 10,000 women who show up to enlist, 9,973 meet the height requirement. There are only 27 women out of every 10,000 who do not meet the height requirement. Does that make sense? Z-scores are used in a variety of situations. Okay, so here's the stuff worked out. See, we got the same z-scores. It's all good. They got the ineligible is 0.28. We got 0.27. Okay. Another example of where z-scores come up. Okay. Lauren and Daniel go to Talawanda High School. When they take the standardized tests, we get an envelope in the mail titled, "To the Parents of Daniel Lemonacker." We just got one. Open it up, and it has printouts in there on how they did on these standardized test scores. And those results are based on state and national standings. Okay? For example, with the math, I was trying to recall, I forget what the numbers were, but let's say that the mean, and they'll tell you on the printout, the mean score, let's say, was a 225. Daniel did real well in his math. Let's say he got a 315. And the standard deviation for this is, let's say, 47. So we open the stuff up, lay it on the counter in the kitchen, and say, there you go, buddy, there's your test scores. What do you think his first question to me is? Did I flunk? Did I do any good? Am I smart? Am I stupid? Okay? And my first comment to him is, dude, you're not stupid, because he's a sophomore and he's finishing off the senior level math. Next year they're going to send him, I guess, to Miami to start taking math classes there. Okay? So, stupid isn't in the realm. Okay, he does some stupid stuff, but it's not math related. He's a sophomore. Okay? Where does this place him, in the state or in the nation? Percentage-wise. That's really what he's after, isn't it? Okay? One of these days, your kiddo's going to be asking that same question. So, what's the deal, Dad? What's the deal, Mom? Where am I? Well, you're in the kitchen. Okay? The Z-score. Draws a blank. The Z-score is whatever the child's score is minus the mean, divide by 47, equals, okay, so let's do it, 315 minus the 225 equals, divided by the 47 equals, a Z-score of, let's say, 1.9. Well, a Z-score of 1.9 means he's going to be on the right-hand side of the curve, doesn't it? That means he's in the upper half, but we already knew that because the score is bigger than the mean. Okay, remember that when we look things up, it goes like this. We're over here somewhere, and let's look up the Z-score for 1.9. For 1.9, what percentile is that? Yeah. Say 97, just to make life easy. Okay? That means that to the left is 97%. That puts him on that score in the top 3%, the other part. Okay. His comment was, how do I get to the 1%, Dad? Get another problem, right? Okay. Does that make sense how to work this stuff out? And you need to understand that the percentile that you get off of the Z-score table gives you one side of the curve. The percentile that remains is the other side of that line. Okay? That said, let's take a look at, we've now looked at, okay, how can you start to describe percentage-wise where's a particular score? But knowing what a score is in and of itself isn't the final goal. Because like with the standardized test scores, what are they really trying to say about a particular student with a test score? Interesting. It's given me something completely different than it's given up there. Okay. There we go. Okay, well, we'll just work with this the way it is. When you hit this part of the movie, understand that it's just doing weird stuff. What you want to be able to do is when you're given a piece of information, you want to be able to make an inference from that information about the performance of something. Let's go back to the tires. When you go into a tire store, they've got tires sitting there on display, and they'll say, here's a 40,000 mile, here's a 50,000, here's a 70,000, here's an 80,000 mile tire. When they hang 70,000 on that tire, what are they suggesting? They're suggesting that you should get about 70,000 miles out of that tire. Does that mean that that's what you're going to get out of that tire? No. It depends on how you take care of your tires. You need to check your tire pressure. Temperatures have gone down. That means tire pressure has gone down. You might be at 20 pounds, which is not good. Your tire should be at what? Right around 32 to 35 pounds. Okay. So check your tire pressure. If your tire pressure is low, it causes the tires to last longer or wear out faster. They wear out faster because the full tire is not in contact with the road, only the edges. Okay? Some people take really careful care to make sure that the pressure is right. They rotate them, they balance them, the whole works, and on a 70,000 mile tire they might get 100,000 miles. That 70,000 on there is suggesting kind of an average. It's inferring something that might be expected to happen. Inference isn't a statement of what the truth is. It's a statement of what things appear are going to happen. For example, Daniel is expected to unload the dishwasher and sweep the kitchen floor. When I walk in the house and I look in, dishwasher's still loaded with clean dishes. Look on the floor and, yeah, this hasn't been swept. And I could infer from that he's been goofing around and playing video games. He's not getting his work done. Does that sound about the right road to take? You know, most days that's completely true. Last winter I walked in the house one day and I looked, yep, dishwasher's not been unloaded. The floor, yeah, it's not been swept. Boy's been goofing off again. And he and Lauren come in, they're just binging off the walls, completely overcharged and more energy than is normal. Did you hear what happened? Did you hear what happened? No, you didn't hear what happened? Dad really didn't hear what happened? Calm down, what happened? Well, it turned out that they got home and Becky called him and said, go out and check the pond. The pond was pretty well frozen over. There was a little open spot in the center. And the neighbor had gone out onto the ice, and guess what he did? Fell through the ice. Now, is it very easy to get out of ice in a pond? No, when you grab it, if you can even grab it, because now it's all wet, and wet ice is really slippery. Okay? If you can even grab it and get your elbows up on it, and you press down, and what happens to the ice? It breaks, and you're back in. Well, what had happened that day is they ran out there, and he was out there in the pond, and he couldn't get out. Okay? So they went through, I've drilled them a zillion times on what you do to rescue somebody who's broken through the ice. Amazingly, they followed the rules. Got him out, got the dog out that he was trying to get out. He said, it was really weird, Dad. He couldn't hardly walk, and he was just kind of muttering. And I said, yeah, that's called hypothermia. He was on the verge of dying. Okay? Okay, so that day I walked in the door. Dishwasher, really? Floor? You got to be kidding. I'm making an inference that the kids have been goofing around. Were they? No, they were doing way more important stuff than emptying a dishwasher and sweeping a floor. So the point of this statistical inference is to be mindful that these directions that the numbers are going to lead you are true most of the time. But they're not always true. Just like looking at the dishwasher definitely did not indicate that Daniel was goofing off that day. I'm glad the dishwasher wasn't unloaded. He had way more important things to do. So realize that as we go through this stuff and we start talking about statistical inference, it's just inferring. You're looking at something and assuming something based on what you see. Things aren't always what they appear. Okay? So keep that in mind. It's not displaying what I wanted to. We will call it quits here for today. Okay? I will see you all on Monday, and I hope you have a terrific weekend.